Okay, so quick time. Okay, so they are right endpoint approximation, left endpoint approximation, midpoint rule, and trapezoid rule. So I'm going to illustrate to you what happened. So we're going to go to Desmos. And I draw on the first period because my thing's not working. So it's much, it's not as effective. So we're going to do it with are you serious? Because your iPad is not connected to internet, but oh, my iPad's not connected to internet. So how does my iPad connect to internet? I don't know. OCPS. Don't know my password. Come on, work. It's working, okay. Okay, so we show you this before, right? That approximation for us like this. Did we show you this before? This is the first time you've seen this? Okay, cool. Then we're gonna do it between 10. I'm gonna choose a function that you're more familiar with. I'm gonna choose x squared plus 1, like this. And I'm gonna change that from 0 to 16, maybe 0 to 50, like this. And I'm going to do it in terms of 4 rectangles. Okay. Have you seen this before? This is the first time you've seen this?
Yes.
Really?
Shapara did it with us last year.
Huh?
Shapara did it with us last year.
Oh, Shapara did? Okay, good. Okay. So the idea of approximation is this. Okay, first of all, let me explain something to you. Let's start with explaining. So this year, you know what? This is a new year. I gotta have a better handwriting. Right? New year, new me. Okay, so now I'm gonna try to have a better approximation. So let's say Riemann sum here. It's gonna be the same as before. Fine, I give up already. Right and approximation. This is gonna take forever, and even that's not much better. 2 and those left end, right? And 3, there was a midpoints. And there's 3, there's 4, there's trapezoid. I don't even know if I spelled trapezoid correctly. Okay, trapezoid rule. Okay, so let's start with a simple stuff. In 4th grade, I learned about this. Actually, I thought it was very stupid, but it's actually very important in here. So in 4th grade, I learned that actually third grade. That just say I have a tree here, right? If I have a tree here, if I have tree every 3 spaces, and not just say if I have 4 trees, how many space between trees? 3 spaces, right? Super easy, right? Now, what if I have 1,000 trees? How many space in between? 1,000 trees lined up, straight lines.
Is it like 999?
999. Why is that? Because it's always among the tree minus 1. Does that make sense? So if we have 4 trees, there's a 3 space. If you have 5 trees, you have 4 space. Does that make sense? So it's always m minus 1. Are you confused? No, it's not. That's not rule. That's just what I learned in 4th grade. It's very, very useful here. So, so they say if you have 50 trees, then you got 49 spaces because you got first tree and last tree is gonna be just even that's 1 space. So it's m minus 1. So among the tree minus 1. Does that make sense so far? Okay. So now let's go back to look at this. And if you have 4 rectangles, now very important, we are using the value between, let's just say between 2 and 4. Let's just say, let's just say between 2 and 4. So that's just because, and here, so between 2 and 4. Okay. So we are approximately finding the area between 2 and 4, use 4 equal rectangles. And if you realize if I use 4 equal rectangles, I need to base my height function based on the function. So I will plug in 4 into the x squared plus 1, so that's going to give me 17. So this point here is going to be 417. Does that make sense? And also this point is 3.5. Why is 3.5? It's 3.5 plug in square is going to be 13.25 plus 1. Right? 4 points. But do you realize I didn't use 2? Because of those 4 spaces, I only can use 4 points out of 5. But in this case, we base on the right end. So we start from the right end approximations. Is this over or under? It's over approximation, right? You got this area come out extra. That's called over approximation. So the first idea is to understand what is over approximation. This is over approximation. Because whatever things that extra here, over there is extra on top of the black line. Does that make sense? That little small triangle that is above the black line, and that's the start with. Now this is the approximation. Now I'm going to show you the left end approximation, so I'm going to click away. Here, sorry, I'm going to do 4 here. This is a right end approximation. I'm going to do left end approximation. Are they over or under? It's under, right? Now, my left end and right end is like this. Now, what happened is, you also need to understand what happened. When does the over approximation or under approximation is based on a couple choices. It's a function increasing, decreasing, or concave up or concave down. What do you think is affecting the over or under approximation here? Increasing and decreasing. Now, if it's a function increasing, if I use left end approximation, is that under approximation or over? Left is under, right? So the way you draw it, you based on the whatever triangle size you draw it, it's very important that you know how to draw. You don't need to draw 10 rectangles. You only need to draw one to really decide are they over or under, or a trapezoid, are they over or under. Okay, so that's the left end. This is what it look like. Are we okay? Do you guys see that? I don't use this value 17 at all. I use this value here. And I use this values. Do you realize I did not use 17? Because there was 5 points I can use. I can only use 4 to determine those height. Are we okay? Now I'm going to show you what happened if I do a midpoint rule. What do you think midpoint rule is going to be over or under? And what do you think it looked like? Huh? A mix of both. Why is that? Now, if you pay attention. Wow, this is actually a good approximation. If you realize that green extra area can go replace to the white part. Does that make sense? And the next green go to the next one, and next one, next one. And that kind of like, not 100% exact, but it's actually pretty good. Now, if you realize, I don't use 4. So for example, between 2 to 4, I will usually use 4, 3.5, 3, and 2.5 if it's the right end. If it's the left end, I will use 2, 2.5, 3, 3.5. Now in this case, what do you think which x value did I use? Between 2 to 4. Which value did I use?
You can only have 3 points, right?
No, 4 points.
Oh.
No? What? The question is, in this case, I don't use the endpoint. I don't use 4, and I don't use 2, and obviously don't use 3, and I don't use 3.5 and 2.5. Which point did I use?
Going in between your left and right values.
Well, not right, your right and left and right, of each rectangle, right? So which value that you would use? The first rectangle. It can be the one on left or right, doesn't matter. 2.5, no. 2.25, good. Good job. 2.25, do you see that? I use the height at 2.25. And I use the height at 2.75. Because I don't use 2.5 or 3, I use middle. Does that make sense? And that's it. I cannot click into it. Okay, so if you realize I don't use 2 or 2.5, I use right middle 2 and 2.5, which is 2.25, 2.75, 3.25, and 3.75. Are we okay? Now the next thing we're going to use is a trapezoid. And we're going to use 4 trapezoid. Now, I just want you to understand this. Whoa. This is a very good approximation, right? Are they over or under?
Maybe like exact.
Really?
Probably a little bit over.
You think a little bit over? You cannot tell?
Lines are curved and it's straight and it's probably putting a lip into it.
Let's zoom in a little bit more. Are they over or under? Now later I'm going to ask you to write down. Right now I just want you to observe, right? We just want to observe they are over approximation. What do you think? Why is over? Is it because function's increasing or decreasing or concave up or concave down? Why do you think it's over in this case?
Wouldn't it maybe be because like trapezoids have like a, in this case it's like an x squared or whatever, so, and the x squared has like a curve to it, but trapezoids have like hard lines, and so it would be diagonal, plus x squared is like a curve to it.
Okay, well, somewhat, almost there. But I might ask questions due to reason increasing, decreasing, or concave up, concave down. Why?
Be the concave up and down.
Concave up and down. Because it's concave up, the way you connect 2 points, right? It's going to be over. Does that make sense? You don't need to draw 10 rectangle to 10 trapezoid to tell me that. You only need to draw 1. If you draw from one point to the other point, you see if they are over or under. We're going to show you how the illustration of that. And that's going to be how you justify on AP exam. Are we okay? Now, how do I make it more accurate if I just stay with the right end? How do I make this more accurate? What I say, if I want to find better area under the curve without no mistakes, what's the best way to do it? How do I change it better here?
Oh, isn't it like use more rectangles so like
Ah,
spaces get small?
more rectangle. Let's use 8. Is that better?
Yes.
Let's change the number to 1,000. And let's move accordingly. And let's stop here. It's pretty good. Even though that there is small thing that is extra, but those teeth can be neglected if I'm going more rectangle. Does that make sense? Good job, Ethan. Is that thinking? That's what makes you get through calculus, and especially on AP exam, not the regular calculus, but if you break up more rectangles, it will be much better approximation as opposed of less rectangle. So the more, better. So what does calculus do? The calculus says if I can break up to infinite among the pieces, I'm gonna get exact area on the curve. Does this make sense? Okay, infinite among the pieces. And you add up each pieces. And that is the definition integral, which is we are not going to cover, but I just want you to understand the big picture. The big picture of integral sign is adding infinite among the rectangles. Now, as far as approximation goes, left end and right end is not as good as the trapezoid or midpoint. Which one's better between trapezoid and midpoint? There is no way to tell. There is no way to tell. It really depends on what a function, so it's a hit and miss. Which one's better? I have no idea. But let's do this. Let's show you how the exact area is. So exact area is 20.666. You see that? The actual value on the bottom? And what is the right end approximation if I break to 1,000 pieces? 20.679. I would say it's pretty good. You're going to say, how accurate is it? It's pretty damn accurate. It's nothing, it's only like what, 1/100th maybe, apart, maybe 200 apart. And that's it. That's break to 1,000 pieces. And let's just use the midpoints. And we're not going to do midpoint by a lot. We're going to do midpoint by 200 pieces. So n equal to 200. You see this? It's already 20.72. Do you guys see that? And if I break to 500 pieces, 20.69. If I break to 800 pieces, it's already pretty accurate. If it's 1,000 pieces, it's almost just as accurate as the other one, actually. So it's actually, oh, sorry, that was a bad illustration. We need to open up this file. See, at here, at midpoint sum is 20.666666. It's more accurate than 20.678. So midpoint is a lot more better.
The trapezoid? Or
We don't know. Let's do trapezoid to 1,000. Let's see. Well, we really can compare. We have to break to 500 pieces to really compare the thing. So let's do 500 point. So this 20.666664. So if you think about it, 500 midpoint is better than 1,000 for the right end. Because right end is 20.69. Do you see that? Oh, if you break to 1,000, if you see this 1,000, you see the right end is 20.678, and midpoint is almost exact, right? But if you break to 500 pieces, so we compare 20.678 to 500 of midpoints, it's already more accurate. Even as much as 300 pieces, it's more accurate than 1,000 pieces, right? Even you can, let's go down to 100 pieces. 100 pieces is already more accurate than 1,000 pieces for the right end. So midpoint is really good, okay? That's compared to the trapezoid. I think they miscalculate this. So trapezoid, they have the wrong thing. Anyway. I'm gonna issue a homework as the test. Actually, I don't know. I don't know yet. Not on this. We don't have any homework now.
So for this lesson, are we going to need to utilize our graphing calculators?
Yeah, oh, by the way, bring graphing calculator from now on every day.
So it's like, I don't think I can do this.
No, but we can do calculations. Bye.